as I'm giving the first talk, I may introduce myself in that case. So I'm Piotr Sulkowski from Warsaw.
Can you speak a bit louder?
Oh, yeah. So I'm Piotr Sulkowski from Warsaw. That's the first talk in this program, so I will start slowly. And the title of the talk is Topological Strings, Nodes, and Quivers. So my general aim is to present some relation of nodes and also topological strings to quivers. And this is the work I have been doing for the last year or maybe a bit more. But before I do that, I'd like to start slowly and summarize some basics of topological string theory, which I am sure many of you know, but maybe also some of you have not been working on that, so I hope it might be a bit useful. So the first part will be a short summary of that, so that maybe it's easier to appreciate these newer results a bit later. So, start with topological strings. One can think of this as a device to count maps from some Riemann surface of some genus, possibly with boundaries. This topological string theory comes into versions either closed or open. So when I talk about the closed one, we have just Riemann surfaces without boundaries. The open one is related to Riemann surfaces with boundaries, and we consider maps from these Riemann surfaces to some target space, which turns out that it must be a Calabi-Yau threefold. And these maps, this count can be formulated either in physical ways or mathematical ones. Mathematically, they are encoded in Gromov-Witten invariants. And physically, they can be expressed as certain amplitudes in some two-dimensional supersymmetric theories. Mathematically, they can be obtained as integrals over the Riemann-Mumford compactification of the moduli space of stable maps. And one can consider such a compactification whose virtual dimension is 0, so then one essentially counts some points, and this gives this Gromov-Witten invariance, like very roughly speaking. And once one knows this invariance, one can construct so-called closed, in case of closed strings, free energy of some genus which is a generating function of all these Gromov-Witten invariants. So one sums over beta, which are in the second homology group of this manifold, and this generating function is typically written like this, whereby this q to power beta, I mean the product of qi to power ni, let's say, such that this beta is a combination of the basis of H2 and each of these qi's encode a Kähler parameter of the corresponding basis element. So this qi can be written as exponent of ti or minus ti. This is the corresponding Kähler parameter. Here I'm talking about the A model, so this Kähler parameter essentially measures the size of a given basis element. So this is genus G free energy.
So Ni is run over Z or Z plus?
Sorry?
The index is ni. Little.
Ni, this I,
Yes.
it goes from 1 to the second Betty number.
But the coefficients.
Ni's, there could be arbitrary. I mean, we consider, in principle, all of those. Yeah. And
not all of these. This is effective classes, right? These are things that for which positive. There's some con.
But
you can consider arbitrary one, but most of them, half of them are 0.
Okay.
So in other words, this doesn't exist.
Yeah. But it's not that we fix them to some specific values. And then it is also useful to assemble all of this GNSG free energy into the full free energy, which is also related to the partition function. So this is this exponent of the free energy, which assembles all of those Fg all together with some coefficient, which is called topological string coupling. I denote it as h bar. And one of the purposes of this topological string theory is to determine those FGs or equivalently those partition functions. And there are various ways to do that. And in particular, we will see how these partition functions can be related to quivers. That's the aim of my talk. And also the open version, I will come to that in a moment, of such partition functions in some specific situations related to knots.
So h to the 2g minus 2, maybe?
2g minus 2, of course, yeah. So this is the genus expansion, and that's right. To give you some example, one of the simplest but also quite instructive, I may consider, in fact, a special case which is also included here. So I can consider this beta to be 0, and I can consider constant maps, which are also a part of these quantities. One can do that for more general geometries, but let me consider the simplest one, C3. Then the result is still non-trivial, and it is given by a so-called Faber-Pandari-Pande formula for those Gromov-Witten invariants, NG0 in this case. And, well, this is some expression given in terms of Bernoulli numbers. It looks complicated at first sight, but it's nice that it can be given for arbitrary G. So this is in fact for G greater or equal to 2. And just as a reminder, these Bernoulli numbers can be defined by the following generating function. So in this case, this Fg are essentially identified with this Ng0, and we have explicit form of this partition function in this genus expansion. And, well, as I say, I have to summarize all things quickly, so I try to review a few different aspects of topological string theory, maybe without giving too many details. But I hope that would be useful. So then there is an interesting observation that this numbers which come from Faber-Pandari-Pande formula are in fact related to the McMahon function. And they arise from the genus expansion of this McMahon function, which is kind of simple. At least it's easy to write it. Looks much simpler than this Faber-Pandari-Pande formula. And this Q is exponent of h bar. And probably, as many of you have heard, this McMahon function counts plane partitions. So these are the objects which you put in a corner of a box. You construct them out of some elementary boxes which you stack on top of each other, but in such a way that if you would put this corner like in the bottom, you would like all these boxes to fall down. So you obtain some shapes. That's one of the simplest. Q is exponent of h bar. You can write several first terms of this generating function. So this one corresponds to the empty configuration. This Q corresponds to this, what I just have here. This is just single configuration with one box. If you have two boxes, you have three configurations because you can put them along each of these axes. So this is this three and so on. If you have six, then you may have either three boxes along each of the axes or this L shape also in three configurations. So it's six and so on. So altogether, you consider like a statistical model of all such plane partitions or three-dimensional Young diagrams, and well, this is the generating function. It came as a kind of surprise that if one considers this h-bar expansion, one gets these contributions. And well, in fact, there is.
Sorry.
Yes.
So you mean that the radial asymptotics of this Q is analytic in the unit disk?
Yes.
And you say its radial asymptotics when Q approaches 1 is this formal?
Yes.
And what happened to zeta of 3 or something?
Zeta of 3.
There will be a leading term.
Yeah, so these are for g greater than equal to. So there is also some f0, f1, which I missed.
Did not write those.
And in fact, this picture is not accidental. I mean, the fact that this McMahon function is somehow related to those Faber-Pandari-Pande formula for C3, because this picture gives these plane partitions a realization of something that is called the quantum structure, or just quantum C3, and this is called also Calabi-Yau crystal for that. As has been discussed in a paper by Okunkov, in Kumbrum Wafa. This was around 2005 or 4, something like. Maybe even 3.
3 or 4.
So the way you can see C3 here is that you think of this C3 as a toric manifold. So it has some three-dimensional real base, and this axis represents these directions in the base. And then over each of these points, you would have some toric, some torus, three-dimensional torus. And then those like crystals are some quantum manifestation of the character of this C3. So that's one essential observation. And another remark I might have, that you can also think of this picture as a very simple example of the structure of those closed topological string partition functions, which is more general and which in fact encodes so-called Gopa-Kumar-Waffa invariants. So maybe I can still fit here. More generally, so this is the observation or statement from the work of Gopa-Kumar and also Kumbun-Waffa in like 99. And the statement is that this partition function in general can be expressed in terms of Q, also defined in this way. And what I'm writing now is essentially a big product of something like this McMahon functions, which we just saw for C3. So just a couple of words about this formula. You see that we have this product over those betas, 2 cycles inside M, and then some J. And for each, if you fix beta and J, you have this product over L's, and the L enters here. This is Q to power L, and also here. So this product over L still looks like this kind of McMahon function, a bit generalized because of this factor here. And then here are the exponents. These are these Gopa-Kumar-Waffa invariants. And they have profound physical interpretation, which I just mentioned in 2 sentences. Namely, one can embed this topological string theory in the full 10-dimensional string theory. And then instead of considering this internal Calabi-Yau space, one can consider the effective theory in like normal 4 dimensions. And then these ends are related to the counting of certain states, which come from deep brains that wrap these cycles that we consider here. So it is not quite trivial to derive this form, but for mathematicians you could just think of this as a certain conjecture, that if you consider this partition function, which you can define mathematically rigorously, then the statement is that it should have this representation. And 2 important points are, first of all, just the structure of this representation. And moreover, on top of that, because these ends, they count those states which are just mentioned, they should be integer. So this is quite a non-trivial statement too. And then around 2000 and several years after 2000, a lot of effort has been put into analyzing various Calabi-Yau manifolds and finding this Gopa-Kumar-Waffa invariants, and indeed showing that they are integer. In very few cases, one can prove it that all of them are integer. In many cases, people could just compute this and BJs up to some degree in beta or up to some genus. There is famous work, in particular by Albrecht Klemm, who computed that up to genus 51 or something like this in some cases. But you see that in particular you might think of this C3 as a particular case of that, and then you would have just a single invariant of this form because we have just a single McMahon factor. But more generally, it's more complicated.
before this McMahon function, it was analytic inside the unit disk. So I can talk about its asymptotics f equal 1. Now this right-hand side, is it an analytic function of Q? Or if not, what does it mean to compare a Q expansion with an H bar? How does a Q expansion gives rise to an H bar expansion?
Well, you can just rewrite this in the exponential form. And
but these are infinite products now.
These are
I worry about product over beta and also J.
It becomes sums. If you take log of it, it becomes sums.
so,
And it will converge. I mean,
We went backwards from the.
so in particular, the leading term, in fact, is a tree logarithm here. So each of those factors gives you, even though product over A is infinite, it gives rise to a single tree logarithm, which is like genus 0 contribution in that genus expansion.
So for any integer values of the BBS invariants, there is an H bar expansion. That's what you're saying.
Well, I'm saying that at least for such values which make somehow sense. If you would take some random collection of this, I'm not sure if that would correspond to some.
But as a formal series, it certainly makes sense. Your question is
Always.
as a formal series, it perfectly makes sense. Term by term, you can get a structure which can be rewritten in that form. Whether or not it makes sense as an analytic function, that's a different question. We're not asking.
Okay, so this was a very brief summary of closed topological strings, and in fact I am interested much more in open topological strings for this talk, but it is useful to maybe introduce that first. And for open topology...
So just roughly, maybe since they're asking, that J in that N, there are two things. There's a beta and there's a J. But roughly speaking, J can be extracted if you compute Fg up to G equals to J. And beta, you have to note for each beta what Fg is. So that, in other words, you can recover these numbers term by term. If you know F up to genus G, you can recover N's up to over their J. Up to over their G. Roughly, that's how you can reconstruct.
Yeah, so you can write explicit formulas how this and beta J's are related to this Gromov-Witten invariant. You can go from one to the other.
So, but for instance, what happens with F0?
It's there. Still.
The coefficient of 1 over H.
Yeah, it would be this tree logarithm that I mentioned. So the leading term of this McMahon function is exponent of 1 over H bar square, and then there is tree logarithm with this argument, which would be genus 0 contribution. Okay, so I am more interested in open topological strings, and then the story is somehow parallel and structure not the same, but somehow similar. And there is also formulation in terms of this genus expansion, but I will not start with that, and I will just continue with this quantum Calabi-Yau picture. So, in fact, this McMahon function is the function in which you consider all these configurations of plane partitions which are arbitrary just at infinity they should go to 0. But it turns out that you can consider, apart from closed topological strings, also open ones, for which you have to specify certain boundary conditions which you can encode, for example, in terms of branes, and then these boundary conditions are encoded in certain two-dimensional partitions which you have to specify at infinity in this crystal picture. So you can consider the generating function of plane partitions, but with this fixed boundary conditions which are labeled by now ordinary Young diagrams P, R, and Q. And such a generating function is called the topological vertex. CPQR is this generating function for fixed PQ and R, and it's also been found like explicit form for that in that work. So it can be expressed in general in terms of skew-Schur functions. I will not write the general formula. But to give you some flavor of that, I will write a formula which we will need later. So if I have just one non-trivial partition and the other two are empty, then this vertex, topological vertex amplitude, reduces just to Schur function in this representation P with the argument, well, there is infinite set of arguments which are Q to various powers, and one can write explicitly how this looks like. Well, not yet. So this is general formula, but now if I would take this P to be just a symmetric representation, so P would be a diagram which is just one row that consists of n boxes, then this is like a sample result. And again, you may think of this as this Calabi-Yau, like some quantum Calabi-Yau, or you can think in terms of the storic picture that I mentioned before, that there you have some base, three-dimensional base, and on top of that torus fibers. And this base you can also represent in terms of two-dimensional picture, which is called a toric diagram. So for C3, this is how this picture looks like. If you have some of these boundary conditions at infinity, you can represent them or encode them in some particular types of branes, which I denote by this additional element in this picture. And they are sometimes referred to alpha branes, and I think it was in 1999 where they were described in detail how to construct them geometrically and so on. So my message now is that this vertex amplitude, which I mentioned here, corresponds to the amplitudes of C3 with three such branes, in fact, labeled like in this picture by P, R, and Q. And we have here one particular example how such a result looks like. And then it is useful to, in fact, consider generating function of these amplitudes, which I will denote by psi of x, and I will call that open topological string partition function. So in this particular example, I can write the generating function, but I can also write it in the product form. This is, of course, very well-known basic formula in Q-series. So this can be written as an infinite product. It was n square half. Just for convenience, I will write the generating parameter here as q to minus 1/2 x, and then raised to power n. So I assemble all of these amplitudes into one generating function, and then in this case they are expressed in terms of a single infinite product, which is also referred to as quantum logarithm. So you might think of this single product as kind of analog of this thing. You see that the only difference is that here is this additional n in this power, which is absent here. And this has also h-bar expansion. This is called quantum logarithm because to the leading order it behaves like exponent 1 over h-bar, and then here is ordinary logarithm of x, and then some higher terms. So this thing under this exponent, this is something like this genus expansion of open topological string. So the analog of that, you see that this first singular term starts as 1 over h-bar, not h-bar squared, so that's the difference, but it is somehow parallel. And also there is analogous structure to this Gopakumar-Vafa expansion for open strings. It is called Oguri-Vafa expansion. Maybe I will try to fit it here because I may need it. So this expansion I am writing now also defines another set of invariants which are also expected to be integer, and they are referred to as Oguri-Vafa invariants, or they are also example of some BPS invariants, or they are also referred to as BPS numbers. And they have analogous interpretation like this BPS states. In this case, one just counts BPS states related to branes which have some boundary, so they are not closed. So here is a product over beta, also over n. And then this product over k, which I have here, gives the structure of, again, quantum logarithm. So these Oguri-Vafa invariants are those numbers which again appear here in this exponent, and this is non-trivial statement that they are integer. And there is some physical picture which tells you that they should be, but again mathematically you could formulate this genus expansion like in the closed string case, and then think of this as a conjecture that you can rewrite it in this form with this integer exponent. So that's kind of a brief summary. And so my main aim for most of the rest of the talk is to understand the structure of this better, and in particular prove that they are integer in some cases. So this conjecture was also formulated in 1999 or 2000. And soon after that, there was a lot of activity where in various examples these n's were determined. They were checked to be integer, but there have not been a general proof that you, for example, for a given event, for a given configuration, that all of these are integers. So that's something I'm interested in. And, well, one important aspect of this open topological string theory is that this is very closely related to nodes. So this is why there is the second term in my title, and of course this is why we are in this program, and so on. And this is something that you in fact already see from this example of C3. So this configuration just with a single brane is in fact closely related to the unknot. This is some particular, this result I have here, this is some particular limit of the colored Humphrey invariance for the unknot. And I will just write a bit more general answer, which is also important for the rest of the talk. So what I'd like to do is to consider the unknot and consider a generating function of colored by symmetric representation. So Sn colored Humphrey PT polynomials which are very well known. So for the unknot, this colored Humphrey PT polynomials take the following form. And in fact, in this particular case, this sum can also be written as a finite number of quantum dilogarithms, just 2. For those of you who are familiar with various Q functions, this statement is called Q binomial theorem. And this is just the result in this case. So this is an example of the situation where you have just 2 Oguri-Vafa invariants because there are just 2 terms. This is a very rare situation. Typically you have infinite number of those. You can, in fact, consider a slightly more general amplitudes or slightly general generalizations of those branes, where you include so-called framing. So it corresponds to some simple geometric operation of those branes. You can change this framing by some integer number. Which in this situation would amount to inserting here a factor which is -1 to power n times f, and then q to n and -1 divided by 2f. But if you would do that, you would then anymore get finite number of quantum dilogarithms. There would be infinite number of those. So to get this finite number, you have to choose this framing quite carefully. But anyway, we see that this structure indeed works, so to say. And it's also useful to consider this unknot because it gives us also some insight why we see not invariants and also why we saw this relation to not invariants even for C-free geometry. And we see those because this unknot amplitude, we can think of them as being related. I mean, this is just the amplitude in another geometry, another toric Calabi-Yau manifold, which is called resolved conifold. And we have this brane attached to one of these intervals. So this resolved conifold arises from gluing 2 C-free patches in some specific way. So you can think of this as having these trivalent vertices corresponding to 2 C-frees. You glue them together, and then because of the toric structure, you know that over each of the edges, in particular over this edge, you have some S1 which has to degenerate at the ends of that. So you have some S2 essentially, a sphere over such a finite integral. So this resolved conifold is also called local P1. And this particular manifold can be related by the process which is called geometric transition to another version of the conifold which is called the deformed conifold, and this is essentially T star S3. So in this process you still get, I mean, this T star S3 is the manifold which is the modification of this resolved conifold, but if you include this brane, it is still here. This is some Lagrangian brane. And this is such that the intersection of this Lagrangian brane together with S3 gives you some closed curve in S3, so essentially a node. And then it also turns out that topological string amplitudes in this setup reduce just to amplitudes in Chern-Simons theory, which are known to compute not invariant. So this is why at the end we get this not invariant in this topological string setup. They come essentially from Chern-Simons theory. I know I am very sketchy here, but I think many of you know that, and those of you who don't, well, this is at least some appetizer why these topological strings are related to Chern-Simons theory. And then expectation values of Wilson loops for nodes gives this invariance. So this is why the relation to nodes arises. And the consequence of all that is that if you study various not invariants, you can view them as particular case of this topological string invariance. And general statement is that for each node you might engineer some appropriate brane, which you could put in the resolved conifold, and then computing topological string amplitudes, which would give you those not invariants, like in this example. So, okay, I think this is the end of the summary of the first two items in the title. And now I'd like to tell you that all of this somehow secretly knows about quivers, or all these invariants that I discussed so far can be captured by theory of quiver representations. So if you like, you might ask some question at this point about whatever I have said. But now I'd like to switch gears a little. And tell you a few words about quiver representations, which physicists probably know from, for example, analyzing quiver gauge theories. And mathematicians know them from analyzing other questions, in particular considering or trying to understand the structure of all linear representations, which means considering some quiver. So a quiver is a set of some vertices with certain labels which mathematically correspond to the rank of certain vector spaces. For my purpose, I just focus on complex vector spaces which can be assigned to each vertex. And then there is a bunch of arrows between vertices. In general, there could be arbitrary number of these. I considered arrows, so they point from one vertex to another one. They have a direction. So let's say I have in general n vertices, and all these can be assembled into one vector, which in this field is called a dimension vector. And so again, these vertices or nodes correspond to vector spaces, and then each arrow is supposed to represent a linear map from one vector space to another one. And what mathematicians are interested in is the structure of the moduli space of all such maps. So let me fix some particular dimension vector, and then schematically this moduli space is the moduli space of all possible maps possibly with some additional conditions like stability conditions, and one could also introduce certain relations or so-called superpotential, which I ignore for a moment. I just have to divide this by this like gauge freedom. So mathematicians would like to see what is the structure of this moduli space. And physically, such moduli space arises as the space of vacua of certain supersymmetric theories. So this is also why this is interesting to physicists. And then, in particular, the structure of this space is encoded in so-called Donaldson-Thomas invariants. Which are, at least roughly speaking, dimensions of the homologies of this space. In some cases, they are very subtle to define, so I'm not going to give formal definitions, but you can think of them as dimensions of homologies or cohomologies of these moduli spaces. And in general, they are quite hard to compute, but there are certain classes of quivers for which you can do that. And there is one particular class I am interested in, which are symmetric quivers. So symmetric quivers are such that if I have an arrow from one vertex to another, I must have another arrow in the opposite direction. So let's say I might have such a configuration. And then these DT invariants, there is a particular way to define them. So what one has to consider is so-called motivic generating function for a quiver. Which depends on as many generating parameters as the number of vertices. And it has some well-defined structure, which is q, well, here is with power 1/2 square root of q, and then raised to a power which is a quadratic in matrix C, which encodes the structure of the quiver. So let me denote by C ij the number of arrows from this vector space, well, from vertex I to vertex j. So this is some symmetric matrix. And this symmetric matrix, so the information about the quiver enters just here in this exponent. In denominator, I have a bunch of q-poch hammers, and then all of these generating parameters x1, d1 up to xn to power dm. And then the statement is that to find this Donaldson-Thomas invariants, or in this particular case they are called motivic Donaldson-Thomas invariants, you have to write this sum in the product form. So you consider all sets of these, just different one than having all of them 0, and they have to be positive. Let me write it like this. Product over J. And then something which again has the structure of quantum dilogarithm. Just in this, now we have this set of generating parameters, q to power k plus j minus 1 divided by 2. And this is raised to a power the power is -1 or +1, and then times this number, which is called Motivik dt invariant. And so it was postulated by Kontsevich and Seiberman that this product structure should be like this, and then this omegas should be integer. And a little later, Efimov proved that these are indeed integer. So all this is around 2010, more or less, plus minus 2 years maybe. And, well, if you are somehow careful, you can now see that the structure of this product is somehow similar to the structure of this Oguri-Vafa expansion. So here we had also this quantum dilogarithm for each of these numbers. We had one quantum dilogarithm, and here this is kind of the same. We have a bunch of quantum dilogarithms and then raised to these powers. So already this suggests that this Motivik dt invariant should be somehow related to this Oguri-Vafa invariant. And what is important also, as I say, these are proofs to be integer. So if one could find direct relation between those n's and omega, this would be a way to prove that those n's are integer, and this is indeed what we did last year, or what we are still working on. But in various cases, in particular for various nodes, we can find explicit identification between these numbers. And if we do that, then we immediately have a proof that for, let's say, a given brain configuration or given node, all of these are integer. So, well, before I go to more complicated examples, I will just show you the simplest one, which in fact relates to simplest things which we already have in the blackboard. So consider the simplest quiver, which is just of size 1. So we have a single vertex, and let's say with some number f loops. In literature, this is also referred to as the f loop quiver. So if you look at this generating function, I can add the label C here because, well, this is assigned to some particular matrix C.
Is that even?
Excuse me?
Do you have even f or not?
No, arbitrary, just integer.
So this was not symmetric in that sense, or you can consider this?
Oh, well, the loops don't come with a direction. In a sense, they go from one vertex to the same one, so I don't need to have another one. So you see that in this case, this PC reduces just to a single sum over these. And this is essentially the same thing as we had here. So this is the same thing as the brain amplitude in C3 in framing F. As I mentioned somewhere here, this framing factor, which you could include, is Q2. In this case, it was n squared times F. So this is precisely what we have here. So we see that this particular quiver corresponds to the framed AM node. So we can again think of the quiver or about this brain in C3 or framed AM node. And once you realize that, you might wonder whether this identification works more general. So let's say for other nodes or for other even more general brane configurations. And this is indeed the case. So there are two ways to...
So let me just make sure. If f is 0...
Well, I may not be very careful with all the conventions here. If f would be 0, in fact, we wouldn't have this thing. So what we would get would be, in fact, inverse quantum dilogarithm.
But the Quiver representation is very boring if it equals 0, no? Am I missing?
Yes, and this is why we would get just a single quantum dilogarithm, which would be...
Why would you get anything? I mean, what is the Darcy-Thomas invariance for trivial one node with no map?
Well, we would get a single one, which would correspond to having this single. These are the Motivik Donaldson Thomas invariants. So there are certain deformation of the ordinary ones. So I suppose that these trivial ones that mean would be this ordinary and this certain deformation.
So again, this f, so f, the framing can be positive and negative, for example, right?
Yes, so from Quiver perspective, it makes sense to have non-negative number of loops. But of course, here you can restrict to just positive framing as well. But in fact, the statement that this expansion has positive exponents works also for negative framing. For sure, there is overlap. You can.
Well, there is some symmetry or something. Right? F to minus f or something. So not some symmetry. It doesn't look like there is one from the formula.
Why? I'm not sure what kind of symmetry.
There's also.
Seem to vaguely remember that there is some symmetry.
I don't think so. At least one counterexample is that if f is 1, this is what we had here. Here we have this 1 factor of n squared. So this is framing 1. In fact, this gives a single quantum dilogarithm. But if we take f to be minus 1, then we would have infinite number of these.
So it's 1 and 0. So when f is 0, there is a single, and when f is 1, there is a single.
In this case, there is, but I don't think it works for other f's. Or at least it's not crucial for what I'm going to say.
I mean, Kumran asked the question about this evenness of f, right? So somehow you have a q to the 1/2, so you have to say something about...
No, but I don't need to have that even. I mean, f is number of loops, but loops...
Is the diagonal in the matrix C? It's the diagonal.
It is diagonal, and I can have. I must have odd. I must have a possibility to have odd numbers on diagonal. I will show in some other example.
But don't you have to say what you do to the square root of q in that case?
Well, this is a bit conventional. Of course, in this case, I have, if I write the square root of 2, I can use another variables where I just have q, and then everything is nice. So.
Well, if you take q to the half to an even number, then you get power of q. If you take q to the half to an odd number, you get to say which square root you take.
So maybe, well, if you wouldn't like to have doubts, it's better if you use q instead of square root of q, and all these formulas you can then write.
So you are using q. Right? You're using q.
Okay, indeed, you're right that I mean, sorry.
You could use square root of q as a variable, but then you still have to say which. You still have to.
That's right. I got confused. That's right, because I have this q-poch hammer here, which is just in terms of q, and here I have q to 1/2, and here I have just. Oh, but here I also have q n square half, right? So, yeah. So this half which is here is the same half which is here. So the framing on here, the framing would come as just f here, which would be just the one I have there. Yeah, so no, I'm not inconsistent. I think this is essentially consistent. Up to, well, maybe some signs which I have not been very careful about, like this one, but I assure you that it all works and can be match to each other. But so my main message is that this simple example which we have for this F-loop quiver can be generalized in fact to different, well, not very different, but somehow you can think of them as different situations. So one of them is just to consider other nodes. So from the viewpoint of topological string theory, you would be considering still a conifold, but with some complicated brain inside that, which would engineer a given node. And this is what we did in a couple of papers last year. This is relation we refer to as the nodes quivers correspondence. And well, to mention just a little piece of literature, we had a paper with my student Piotr Sulkowski and Markus Reinecke and Marko Stosic. We had two papers. And we also had a paper with Miłosz Panfil, who's postdoc in Warsaw, and also Marko. This was in February this year, and there was yet another paper just by Marko and Paul Wedrich in November. So in these papers we show that this relation between quivers and nodes works much more generally, and we identify quivers for various nodes and various examples of nodes. If I have time, I will give you some list, but let me just say that it works in that context. So this is one direction of generalization. And recently we noticed that we can generalize this also a bit differently, in the sense that instead of taking more complicated brain, we consider more complicated Calabi-Yau manifold. So we still keep this kind of simple Arganidis-Vafa brain, but we can consider other manifolds like those toric manifolds whose diagrams are composition of this toric diagram for C3, but oops, I lost the microphone. Sometimes they are referred to as generalized conifolds. So let me just draw some example. For example, you might have such a diagram. This is some more complicated toric manifold with this brain. And for all these geometries, which also find underlying quivers, and then this in particular immediately proves that the Oguri-Vafa invariants are integer for these geometries. So this is basic idea of this correspondence between nodes or topological strings and quivers. Maybe I can also summarize various objects on both sides of that which are mapped to each other. Or maybe before I do that, let me just draw some pictures so that you have some better idea what objects you have to deal with. So I already gave one example, which is this F-loop quiver, which corresponds to this simple brain in C3 or just the add node. But let me give you some more complicated one. So if we think of nodes, you may take next to simplest node, which is trefoil. There's something wrong. So that's trefoil. And in this case, the corresponding quiver looks like this. And it has 0 loops here, but 2 loops here, and 3 loops here. That's one example. Or another example in the spirit of the second arrow. Let me take some other toric geometry which looks like, well, toric diagram is like this. And I have this brain here. So in this case, the quiver that I get, in fact, this is disconnected. Now I can consider arbitrary framing, so I have f plus 1 loops on this arrow, and I have 2 other vertices which are disconnected. Here is one loop. So these are a kind of quiver diagrams that we get, at least in the simplest situations. And let me write also some quantities or objects on both sides of this correspondence which correspond to each other. So here we have nodes or topological strings, and here we have quivers and the representations. And the things that we can match are, well, some of them you see directly. So for example, if you look at the quiver, you see what is the number of loops and arrows. And it turns out that they correspond to framing on this side. This is what we already saw, at least in some examples. And in particular, in case of nodes, they correspond to something that is called homological degrees. I'm not sure if I will have enough time to present in detail what they are, but maybe I will just give some example. Then in the quiver we have also vertices which in case of nodes corresponds to homology generators. So these are generators of the Hom-Flippity homology. And in case of this toric manifolds, we see also very nice interpretation of what these vertices are. They seem to correspond to kind of fundamental disks which are associated to each of this picture. So each of these manifolds is made of several of these local P1s. So each local P1s come with 2 basic disks, which are those which also appear in this partition function for the conifold, which I wrote earlier. And there is one more related to this brain. So we immediately see what is the size of the quiver for all these geometries. And for nodes it is a bit less trivial, but if you know what is this homology, then you also see immediately the size of the quiver. And then there are more involved objects. So we have these open partition functions. Which for nodes take form of generating functions of colored Hom-Flip polynomials. And they are related to this motivic generating series. And then we have this BPS invariant, which for nodes are referred to as LMOV, Labastida Marinho Gurivafa invariants, which are mapped to this motivic DT invariants. And well, that was one of the motivation for our work, because if you know that these are integer, once we relate this to this, we get the proof that these BPS invariants are integer. So that's quite nice. And then, well, I hope you can still see. If you don't, then you can let me know. But I still try to fit here 1 or 2 lines. So one thing which has been expected to exist for many years on the side of the string theory side is the algebra of BPS states. Which on the Quiver side can be identified with something that is called cohomological whole algebra. That's too long. And well, finally, you might think of this whole moduli space of Quiver representation as a kind of new invariant which you can associate to a knot or to some brain configuration. So this could be some example, hopefully, of categorification, in the sense that instead of assigning some numerical invariants to some object, we assign some geometric space, and then different characteristic of this space, like homology groups or dimensions and so on, are related to numerical invariants that we knew before. Okay, so that's general idea and this correspondence between different objects. And now I'm not sure how much longer I should speak, because we have the room for 90 minutes and well, there are like 15 minutes left, but you might have some questions, or I could still provide some examples. I'm not sure what is the best plan.
Can you say more about the second line there?
The second line, it's vertices, you mean? Or?
But also the second,
Oh, this second line. You mean?
This second line and also the other second line that you just...
You mean this relation to this other manifolds?
What is this manifold on the left and what's the quiver on the right?
So, well, this toric manifold, so the second line is, so I didn't in fact mention that.
Are you saying that these quivers appear more generally than just for knots?
Exactly, that's what I meant here, that
sorry.
we have these two ways of generalizing that. One is to consider still the conifold, but more general brane, which encodes more complicated knots. This is one direction, which is what we did in these papers like last year. And now we have a paper which is about to come, maybe even in the next few days, with Miłosz Panfil and just myself. And then we show that we can consider more general toric manifolds and also branes in more general toric manifolds, for which also we can find quivers, and then this proves integrality of Oguri-Waffa invariants. So this class of, so let me now focus.
So can you say, for example, in this example, how this correspondence between the vertices and the disks works?
Yeah. This is just what I think I can erase that. So this, maybe let me draw a more general picture of these geometries. I mentioned that briefly, but let me say again. Okay, here we have a nice line, so let me use this one. These geometries are called sometimes strip manifolds or strip geometries, because we consider a strip like this one, some triangulation of that, and then the toric diagram that we want to get is a dual diagram. Maybe I use another color. All right, and here I have this brane. So this manifold arises from gluing several C3 patches, similarly like for the conifold. So the diagram for the conifold is just this one. It comes from gluing two C3 patches and two vertices. Here I have just more vertices, but this is just some toric manifold with a brane. And then if I would have just a single P1 here, if I would focus just on this piece, I know that at least in some framing I have two Oguri-Vafa invariants, which if I have brain embedded in that corresponds to two disks from two hemispheres which end on that brain. And
confining only to unknown.
It appears to the unknown, but I mean, what I say, we don't have very rigorous mathematical formulation of that, but we just see that the size of the quiver is 2 times the number of those S2s, let me say, and +1, where the +1 would be a disk coming from associated to this brain. So this seems to be, I could write the matrix which encodes this quiver. Well, this is just some symmetric matrix. But its size seems to be, at least this is quite natural to expect that it should correspond to those two cycles.
But why does it have disconnected pieces? I mean, this sounds so strange.
For the quiver, well, it comes. So to get this quiver, we do.
What does it actually do to this? Doesn't this DT generating series factorize when you have a disconnected quiver?
Yes. Yeah. It factorizes.
It factorizes, but the partition function for this geometry does not factorize. Right? If this geometry is.
Well, it factorizes, but in somehow strange way. It's a bit technical. So you can identify some factors, but they do not depend on the brain parameter. So we have this, let me say, x, which is brain modulus. A part of that, we have a number of the scalar parameters. So it factorizes in a way that some quantum logarithm, which depends just on the scalar parameters, appears as a factor, and this is what corresponds to this isolated vertices. It's a bit technical. Maybe if I would show more exact formulas, it would be easier. Maybe what I should say still about this structure once we discuss it is what is the partition function in this way, because it is also quite nice result, which is a generalization of something that is called generalized Q-hypergeometric function. So here I have this framing factor. In the conventions I use this is raised to power f plus 1. But then I have x to power n, q, n, and a bunch of Q-Poch hammers in numerator and denominator. So there are r plus s of these Q-Poch hammers, and all alpha I and beta j, they are expressed in terms of the scalar parameters qi. It's just convenient to write it in this form, but there is an explicit way how this alpha and beta is dependent on q. So this is how this partition function looks like, and in particular for f equal to s minus r, we have this I goes from 1 to r and j goes from 1 to s. So we have r plus s of these two cycles. If f is equal s minus 2r, then this psi is something that is called generalized Q-hypergeometric function. Denoted like this, which is very quite extensively studied in literature, but it seems to me that it was not known before that this function has this product decomposition into quantum logarithms. And now we see that it must have, because this just arises as a particular case of brain partition function, so there are all these BPS invariants behind that. And this function, in some limits, reduces to ordinary generalized hypergeometric function. So if you are interested in the theory of hypergeometric functions, this result might be somehow interesting. I hope so. And also what we do in this case is that we can write explicit formulas for all these BPS invariants. And they are a bit complicated, so I will not write them down, but let me just say that we have, not just numerically, but we have just in one line write expression for any of these geometries, all classical Oguri-Rafa invariants. We have explicit. Oguri-Rafa invariants. And what is quite nice that these formulas gives also a nice statements in number theory related to integrality. And this is also related to some work that we did with Stavros a few years ago, namely these formulas, well, these omegas that we get in this case. They have several labels, so these labels are related to, there is one number related to this brain, and then a bunch of labels related to all those scalar parameters. So, without coming into too much details, they are given as 1 over n, and then some summations with, well, here is some I, and there are some Möbius functions which enter in these summations and so on. But what is important is that here we have 1 over n, and this result is expected to be integer, or we prove that this is integer by this relation to dt invariants. But as such, this is just a statement in number theory that some combinations of some complicated factors here are divisible by n, because the result must be integer, and we get a very large class of such statements. So a few years ago with Stavros, we had also an example of such structure just for the twist knots or the unknot, framed unknot, and now we have generalization of that to all such geometries.
What happens to the links?
Well, that's more complicated. We are thinking of that, but for links you have more components, or you have more, they are not just labeled by a single integer like the symmetric representations, because each component of a link has to be colored independently. So this is a bit similar like considering representations which are not just one row but several rows. So I cannot say much about that. Of course, we very much hope.
In the toric language, you have probably some handle on off link, right? So.
Yeah, sure. But of course, the simplest case would be to consider Hopf-link with two components labeled by just two symmetric representations. But even this is not that trivial to write in the Quiver form. What we can do, indeed, we can consider links where all component is colored by the same representation. And in that case, we can find quivers. So, for example, there is this series of 2p torus links. So, in this case, if they are colored, all components by the same color, then we can find the quiver. Well, so once I said a few words about the second line, and you see the example of this partition functions, then we get and so on, this statement of integrality. Maybe to conclude, I will just list something related to the first line. I promised before I could tell you for which knots we see that this correspondence works. So we see that it works. So far, what we managed to analyze are all knots up to 6 crossings.
So does this always that the crossing number or the right of the node will be the number of vertices? Will it be true or not? In the quiver? The right on the nodes, the number of crossings in the node, will it also be the number of vertices on the quiver?
No, it's not so. So as I mentioned before, the number of vertices in a quiver is the number of homology generators, Humphrey homology. But it is not related to the number of crossings. For the trefoil, this is kind of accidental. Okay, or twist nodes. And some infinite families of torus nodes like 2,p or 3,p torus nodes. And then in this paper by Marko Stosic and Paul Vedrich, they proved that there are quivers and they have some algorithm to find them for all rational nodes. So this is also some infinite class of nodes labeled by two integers p and q, or by a fractional number p over q between 0 and 1. So for all these examples, we have proven that these quivers exist, and then we have all these consequences in that paper. All right, so I think this is all I can say in this time I am allowed to. And also we are allowed to use this room, I think, until now, because there is some discussion probably from the second program. So, well, thank you, I think.
And there are relation between torus nodes and Hilbert's scheme of points on C2. Is it possible to recognize these Quiver diagrams in terms of Hilbert's scheme of points on C2?
I'm not sure. I heard of this, and there is this parallel work that like Hans Heubelmann or even these people have been doing. I think it's related to this Hilbert, but I cannot say how it relates to what we do. Okay.